today we're going to be talking about servo welding, specifically when to use servo welding technologies versus pneumatic welding technologies. So pneumatic is kind of the standard out there in the industry, with servo welding being a newer technology. It's been around for several years now, but continue to perfect that. So Dukane has what's called melt match technology. It's a patented technology, which is essentially a feedback loop that helps to manage the collapse of the welding of the plastic during the welding process. So it is some pretty cool stuff. My name is Russ Sorrells. So we got Chris Mullins on here. I see Vicky Meza's on here. Mike Dorsey is also a part of our team. CapEx, we are manufacturers representatives, and our mission is to deliver value to our customers. We always want to be adding value. We don't want to just go out there and try to sell equipment. We don't want to show up when you need something. We want to be there to support you before, during, and after the process of implementing capital equipment. We focus on leak test equipment. We represent Cincinnati Test Systems, the largest leak test company in the world. ATC Automation out of Cookeville, Tennessee. They are a turnkey automation integrator out of Cookeville. We've got over 400 employees, just a wonderful company to work with as well. And then we also obviously represent Dukane, and that's what we're going to be talking through today. We got Mark Iannantuoni on from Dukane. He's been with Dukane for many, many years. He's going to walk us through and talk us through the servo versus pneumatic welding. So this is kind of, if you're new to ultrasonic welding, this is going to be a little bit of more of an advanced conversation, as opposed to just talking about what ultrasonics are, how they work, and how to implement them. This is more advanced in the fact that we're trying to understand which applications are best suited for the servo technology versus the pneumatic technology, and how to decide that. So Mark, so appreciative of you joining us today. I will allow you to obviously talk a little bit about yourself, and then share your screen.
Excellent. Well, thank you, Russ. I will throw this up here. And yeah, so I am the regional manager for Dukane. I've been with Dukane coming up on 15 years now. And my region, I'm a Northeast regional manager, and we've got from Maine down to South Carolina, and I also cover the Caribbean. But
Caribbean,
primarily in the winter time, I cover the.
Oh, okay.
No, I do. I really do carry. I do really do cover the Caribbean, but it's weird that my trips usually focus around February to go down there.
Yeah,
let me know if you need some support.
Yeah, if you need someone to carry your suitcase, I think you got some volunteers.
All right, let me get started here. So yeah, the purpose of this presentation really is to kind of go through the differences between the Dukane IQ servo-controlled welders, which feature our melt match technology, and what that melt match technology really brings to the table when it comes to improving your process, improving your welds. So let's get rolling here. So there's our Dukane welder. Real briefly, ultrasonic welding, as a downward force is applied, we've got up and down vibrations coming off of the ultrasonic tool, and that is creating friction between your plastic parts, which in turn creates heat. That gives us the heat available to melt the plastic, and then we squeeze the molten parts together. Seems really simple, but when you're getting into more complex parts, the control beyond that is really important. So again, real quickly, typical 20 kilohertz generator, power supply, and stack. Just to give you an idea of how we're creating this vibration, we're bringing 50, 60 hertz of 120 to 240 volts AC into our generator. We're creating a 20 kilohertz signal at 1300 volts, which is going to our transducer. The transducer has got piezoelectric ceramics that are compressed between two components, a front slug and a back slug. When we pass electricity across those piezoelectric ceramics, it creates a vibration at that 20 kilohertz frequency. We then take that vibration and amplify it.
So that's just to clarify there for everyone, that's 20,000 times it is extending and contracting in 1 second. Correct?
That's correct. That's correct. And we'll all often talk about, when we get into some of these applications, the shorter the amount of time that I'm on the part, the better. And at 20,000 vibrations a second, even a tenth of a second means 2,000 less vibrations that the part sees. So, once you're beyond the melt and you start, getting some other unwanted issues, anything that you can do to minimize the amount of actual time that you're in contact with the part, the better. And again, 2,000 vibrations can make a big difference to something negative that could potentially be happening after the weld joint is complete. So again, just kind of a real brief summary. We've got our ultrasonic transducer that's taking 20 microns or 8 10,000ths of peak-to-peak amplitude on the face of it. We then amplify that through purely mechanical means. So the booster has got a mass that's above and below the nodal point. The difference in that mass gives us gain. So we've got 20 microns coming into one side. If it's a 2-to-1 ratio booster, we've got 40 microns of amplitude coming off the other side. Again, amplitude is variable, but the frequency is always fixed. So we're always talking 20 kilohertz, but what we're trying to do is get more amplitude at the face of the horn. The more amplitude, the further back and forth we're moving, the more quickly we're going to build up heat. Exactly. And Russ, your hands are perfect. So this is just another quick little slide that kind of shows how this gain works. You see the transducer at the top with the piezoelectric ceramics. The ceramics in the transducer are the nodal point. And then we've got our antinodes, the back slug on the transducer and the front slug on the transducer represent the two antinodes at the very faces of them. So you've got, again, at the interface between the transducer and booster, you've got 20 microns of peak-to-peak amplitude at 20 kilohertz that's coming off of it. It's being amplified through that mechanical means of a mass above and below the nodal point. So that 20 microns, it doesn't show it in this picture, but that 20 microns is obviously getting larger. Again, let's say it's 2-to-1, you got 40 microns here. The horn works exactly the same way. It's also got a gain factor based on the mass relationship above and below this nodal point, which is, again, in the center of the horn, more or less. So we'll take that 40 microns that's coming off the face of the booster. Let's say that the horn has a 3-to-1 gain. You've got then 120 microns of peak-to-peak amplitude at the face of the horn. Real basic stuff, just to understand how that vibration works and what's going on here. How is the weld?
I've got a question for you.
Yeah, hit me, Chris.
So obviously you said that the frequency is fixed and the amplitude is variable. When we, interface with the power supply to say, set it to 90% amplitude, 80% amplitude, what have you, what's actually happening?
Right, that's a great question. So we're actually producing we're through a decrease in power going into this transducer. So if we go back to this slide, you can see we've got 1300 volts going in. That voltage actually has an impact on the amplitude. So if we reduce the voltage going in, we can actually adjust the amplitude coming off the face of this. So in 1% increments, we can take that 20 microns and bring it down, by 1% at a time. So 18 microns, 16 microns, 14 microns, et cetera, in 1% increments. So you're reducing the input amplitude and therefore reducing the output amplitude. And again, generally we want to build and design a stack that's got slightly more amplitude than we need, and then fine tune it using that amplitude adjustment.
Awesome, thanks.
Sure. So let's get to this next one. Okay. So this is just a quick little demonstration of how the weld is achieved. You've got your parts in a fixture. The horn comes down, makes contact with the part. We drew a little energy director there to represent the energy director in your parts. Horn comes down, contacts the parts. Ultrasound comes on. It melts that little energy director. We sit on the part for a short amount of time afterwards for hold, for that plastic to reset, and then the horn retracts. The basics of this process, how we do it with a servo versus how we do it with pneumatics actually is pretty dramatically different. So that's really the focus of what I want to do here. One more slide just to go through how amplitude works and how this horn is vibrating. This, hopefully you can see the little animation, shows how everything is stretching and compressing from the blue nodal point, the dark blue nodal point, and your amplitude is basically the horn is retracting and going forward by some number of microns, and that's the vibration that we're talking about.
And the nodal point is the center of the mass, correct? I mean,
right, approximately the center of the mass. It's on a roughly halfway down the horn is where it is. It can change slightly depending on certain horn designs, but roughly halfway down. Okay, so again, we're going to break the weld process into these 4 parts: the pre-weld, the transition, when the material is molten, and then the post-weld. Okay, and I want to kind of go through each of these to explain what the servo welder brings to the table to improve each of these parts of the process. So how a weld is achieved: you've got your normal trigger point, and that's the moment that the machine starts measurement. It's also the moment at which the ultrasound is turned on. Well, that's not always the case. We can pre-trigger, but let's just, for argument's sake and for energy director processing, it's the moment that the ultrasound turns on as well. So you can see the parts are in the fixture on the left. The horn comes down, it makes contact with the parts. After some amount of force, and in this instance, we've got 40 pounds of force set to be the trigger force, that's when the ultrasound is turned on, and it's when we start counting, whether it's counting by distance, whether it's counting how much energy goes into this part, whether it's saying how much time we're on the part. We're going to start our count from that trigger point, okay? So with a pneumatic welder, that trigger point is determined, based on some things going on. So you've got a pneumatic welder, you're going to hit your palm switches or send a start signal. It's going to turn the valve over, and that cylinder is going to drive that horn down at some speed based on some velocity based on the air pressure and the flow control setting. And it then comes down and hits the part. So if you've got a particularly high volume operation and you need to go fast through this process, you can actually hit your plastic with some pretty good initial forces. Those initial forces can actually create some problems. So what we do with ours, and you can imagine, the plastic is compliable. So if you come down and hit it really hard, your trigger point can happen, and then you can actually keep traveling through without melting anything. You're just compressing plastic. What we want to do is we want to make sure that we know exactly where that trigger point is accurately and consistently. So we set what we call our sensing start position. With the servo, we drive the horn down very quickly to a point just above where we expect the parts to be. We can make this position very, very close to the parts if necessary to, again, improve throughput and reduce cycle time. And again, the more consistent your parts are, the closer we can get to them in the fixture. So I've had sensing start positions as little as 3 or 4 thousandths above where the actual parts should be in the fixture, and then we slow down from 4 to 7 inches per second, depending on the press that we're using, down to 20 to 70 thousandths of an inch per second for our sensing speed. So we come down very quickly and then slow down so that we're very consistently and gently building up that trigger force, so that our position at trigger becomes a very, very repeatable and known number, essentially within the tolerance of your plastic. So if your plastic is got a height tolerance of ±2 on each part, then when you look at the data, your position at trigger should be within that 4 thousandths window that the plastic is created. You don't have any bouncing, you don't have any inconsistencies that you see all of that with pneumatic welding. So again, we're starting from a very known, very consistent point, and then going from there. So we've got the parts in the fixture, we've got the horn contact now we're in the weld phase, okay? We quickly transition from 1 to 2. So again, that sensing start position is a big improvement on number 1. Now we're going to go through the improvements on numbers 2 and 3. So I'm going to assume we're going to weld by distance in this example, and we've got our normal trigger point. So we're going to want to collapse that energy director. We generally look for about 80 to 90% of the designed energy director height. Let's, for sake of argument, say that we're going to collapse 15 thousandths in this example. So once we've made contact, we know that we've made a consistent point of contact and a consistent trigger point. Now we know what our energy director height should be, and we're going to collapse a certain amount of that energy director. So during the weld phase, we've got the 2 different portions, and you can see in our graph, we're going to start this from start of weld, and then this is where so we're looking at this section of the graph from one arrow to the other. So this arrow on the right is showing the whole time what happens after the weld, but it's all this graph between 0 and it looks like about 100 milliseconds here is the weld portion that we're looking at in stages 2 and 3. So in stage 2, the transition period, so we've got this horns coming down, making contact with the parts. We've got our trigger position. Now we're going to talk a little bit about melt detect. So when you enable melt detect on the servo welder, we have turned ultrasound on because we made our trigger force, but we don't move. With a pneumatic welder, everything is dynamic. You can't stop this process. It's just going to collapse as the plastic allows. But with the servo welder, we can stop and we can make sure that things are happening the way we expect them to happen before we start moving again. So we've got, in this instance, our melt detect turned on, and with melt detect, we have got an amount of force that we can look for to fall away. So this percentage kind of depends on the trigger force you're using, how big the parts are. There's a few different considerations we make when determining how much that percentage should be, but we usually have that all set for you when we're setting up your process for you. And but it needs to be something. We've done a bunch of experiments and found that without any melt detect, the overall strength and the consistency of the parts is way more variable and way less strong than when we've got some melt detect enabled. And again, it's a pause, and when you look at the graphs, it's typically a very brief pause. You're only talking tens of milliseconds of time where you're looking for that force to drop. So in the example we had before, we've got a 40-pound trigger on this, so we're looking for that force to drop by 2%. And once that drops by that small percentage, then we start moving again. So, and basically we know that the plastic is melted because the force has dropped, because the only reason for that force to drop is because the floor dropped out from under it. So we've got everything under compression. We've got ultrasound turning on. When ultrasound turns on, you typically see a little bit of an increase in force. And the only reason for that force to drop at all is because the plastic has started melting. Okay.
Makes sense.
So again, now we're optimizing this the transition and molten phase. We talked about melt detect, start motion after the force drop. Now we're going to talk a little bit about melt match. Okay, so once we've got this plastic molten, now how do we travel that 15 thousandths? Do we go at a constant velocity, or do we profile the velocity? We've got a 0.5 millisecond sampling rate on our generator, and that is important to this whole process. We need to be able to know exactly what's going on at a very high clarity level, so that we can adjust things and move things according to what the servo itself can do. So we've had this 0.5 millisecond sampling rate for a very long time. Well before we had the servo welder as an option, knowing that we wanted to at some point control a servo, and that the only way to do that properly was with this kind of a sampling rate. So with that sampling rate, we can actually adjust this speed and this velocity in a profile. So in 15 thousandths of collapse distance, we can make up to 10 adjustments to that velocity as needed to make sure, and I'm going to go through in a couple slides why that would be and what the benefits of doing that are. For most applications, I actually set these up to use a constant speed. With a constant speed, you can usually get sufficient strength and well beyond what's needed for these applications, but every now and again there's an application where using a profiled velocity really has some benefits. So in this instance, we've got a constant velocity set of 0.254 millimeters per second, and that's perfectly acceptable, and a lot of applications that's what we've got set. Again, this is a constant servo speed control. Now, when we go into a profiled speed control, like is shown here, we actually can adjust these, and here are the 10 segments. So we can start off at 0.25 millimeters per second squared and increase that as needed. So we've got this molten plastic, and we go faster. We can go slower. We can do a parabolic speed profile, again, depending on the application and what the benefits are. So I've got a few slides here that show the benefits. So this was some parts that we welded with a 1 millimeter per second constant velocity, and it's showing the penetration of this is the heat affected zone, 361 microns of heat affected zone on either side of this assembly. And we did some pull testing on it. We got a 2,432 Newton break force. So that's where the joint broke. Under polarized light, you can see that heat affected zone is relatively small. And I'm going to go back and forth to these slides so you can kind of see the differences a little bit better. So again, this is 1 millimeter per second constant velocity.
So that would represent a pneumatic.
Well, no, that still represents servo, but that
still represents servo. Okay.
Again, that's a constant velocity, and again, for many applications, this 2,400 Newton pull strength is sufficient, and we don't need to go any further than that, and it works quite well. But okay, there's some instances where we want to try and get more out of this joint than that. And so this was a constant velocity profile. This is half the speed. So we went 0.5 millimeters per second instead of the 1 millimeter per second. You can see that the weld penetration got further into this joint. We had a failure load from, and I'll go back again. So we went from 2,400 Newtons to 3,200 Newtons. Again, from 1 millimeter per second to 0.5 millimeter per second. And you can see the increased area. What's important to note here, though, is you can't really adjust this velocity on a pneumatic welder. You can adjust your flow control and you can adjust your pressure, but the plastic is ultimately going to determine how fast you can go. Mm-hmm. You can apply so much pressure that you're going much faster, but you're not impacting this heat affected zone as well and as consistently. You're just kind of plowing through the plastic and generally just cold forming it. With the servo, because I can very accurately and consistently adjust that velocity, I'm actually having a direct impact on the heat zone. So again, this is a polarized image, and you can see that the heat zone on the right there has gotten much deeper into the plastic than the one previous. So now this last slide shows some weld processing optimization. So we've linearly increased the velocity profile from 0.25 millimeters to 0.4 millimeters per second. The melt penetration now has gone from, the last one was 379 microns. We've almost doubled that at 690 microns. So you can see we've gotten much deeper into the plastic. And now our failure is 5,200 Newtons. And
that's again, double. That is double what it was. So it was 2,400.
Yep, double what it was at the beginning, 2,400 Newtons, and we go up to 5,200 Newtons here. So significant force or significant pull force improvements can be made using this process, and The nice thing about the servo is you make a change to that velocity and you see the results immediately. It's not a, well, should I, adjust the flow control a little bit? Should I increase the pressure a little bit? Does it give me the expected results? I've run too many pneumatic welding processes in my time to know that it almost never follows exactly what you expect it to follow. It takes a lot of trial and error. With the servo, we get there so quickly and so easily comparatively. This next slide, I just wanted to show you, what the results are that we see in these. So this is a shear joint on the right, just to kind of give you an idea of what that heat affected zone looks like, where the green and white mix. But the important thing here is this little table. So this table is data we got from one of our customers. So we welded some of their parts on a servo welder. They welded some of their parts on our servo welder, and they welded some of their parts on our pneumatic welder. And they did pull test study. And we've repeated this time and time again, but this was one that the customer was willing to do it for us to gather this information, be a little bit more objective. And what they found and what we've seen time and time again is these pull test standard deviations go from, 6% standard deviation pneumatic is not uncommon, down to 1 to 2 standard deviations on servo. So your pull strength becomes extremely consistent. You do not have the variability in that pull strength anymore. And I like to say with the servo, we've basically eliminated all of the variability of the process itself. All that's left is the variability of the plastic, and I can't do anything about that. So that's on your molder. Now we get into the last part of this, which is the post weld. So we're talking about hold here, and sorry about the phone ringing in the background. In post welds, we are with a pneumatic welder. Again, it's always dynamic. You're always squeezing plastic. You're always compressing. You're always collapsing. With servo, we can stop. So we've basically broken our weld into 2 portions. We've got our dynamic hold, and in this instance, we've disabled it, but you can still hold and collapse for a small amount of collapse distance. So it's not atypical for us to go to collapse another, 1 to 2 thousandths of collapse distance while that plastic is still molten. I can speed up from what I was just welding at and squeeze that last little bit of plastic into its final form for that little bit of time, and then we go into a static hold. So again, you can see here post weld, I've got a weld distance of 0.025 millimeters, so I'm squeezing it a little bit. My weld speed is 1 millimeter per second. My hold speed is 1 millimeter per second. My weld speed was 0.2 millimeters per second, 0.203 millimeters per second. So you can see I'm speeding up this last little bit of plastic. I'm squeezing it really quickly before it completely solidifies. But then I'm going to sit and not move any further. I'm going to sit stationary. We've done a bunch of studies on this as well, and what we found is that by doing this, we eliminate all of the stresses that you typically see that's created by this dynamic hold. All the stresses are eliminated from the plastic, where you just melted, reformed this material. Now you are squeezing it and then breaking those bonds that you just created. By not collapsing any further, we don't add that stress into the joint, and it ends up being, again, a much stronger joint in the long run. This is the other thing that's really important, is the standard deviation of the weld distance. So we can hold much tighter, much more consistent overall heights on these parts because we don't have anything dynamic. We are stopping when we need to stop. We are moving when we need to move, and we're adjusting that velocity when we need to adjust it. Just 2 more slides. I know I'm getting to the end here. This just kind of shows some basics of where we've come from and where we've gone with ultrasonic welding. This kind of goes through some of our history of what you see typically with some of the components in ultrasonic welders. Trigger being determined by a spring force is, these old welders had trigger knobs, and you'd adjust spring force, and you can see the improved control you have over each section of this weld process, each of those four components of the weld process that you have using our servo welder, obviously having force transducers and linear encoders as well included in the press, which is always included on a servo welder, and then the ability to use melt match and melt detect and all of the other benefits that I just went through. Last slide is just kind of going through some of our patents. We're pretty proud of these patents. We've done a lot of work on not just the equipment, but on the process. We have patented many of these features, which I just went through, and these patents enable us to provide something that really no other competitor of ours can. It's and that control of that process and each part of that process has a direct impact to the overall strength and consistency of the parts. I'm yet to find an application done on a servo welder that isn't either stronger or more consistent or both than an application that I've run on a pneumatic welder. Every single time, every single one.
Wow.
Mark,
Well,
I think it's also important to point out that, you know, our servo system has been in production and being sold out to the market for over 10 years now. And obviously these patents still apply. We're just now starting to see some of the competition come out with some of their servo solutions. And, you know, effectively we've got a 10+ year head start on the technology and really have dialed it in. So
Chris, that's an excellent point. And you know, in addition to the technology itself, it's the applications. When you've got 10 years of application experience using a servo welder, and there's a lot of things that we know now that we didn't know 10, 11 years ago when we were first, you know, bringing this welder out. We've learned a lot of you know, we really know how to drive this car. You know, I feel like we're IndyCar racers now instead of driving on a dirt track in our backyard. We really understand the applications and how the tweaks to this process that we can only do with our servo welder really improve the overall strength and the overall consistency.
In talking about applications, let me ask you this question, Mark. Which applications are ideal? I know there are a myriad of applications, but if we're one versus, so pneumatic versus servo, where would we look to apply those variables or various technologies?
So quite honestly, I have found, you know, my original response to that would have been, you know, any hard plastic applications are going to have some benefit. I've actually seen where there's film and fabric applications where we're bonding and cutting and sealing, you know, non-woven materials and things like that, where the servo technology has done wonders. Our ultrasonic cut and seal applications, specifically in the film and fabric realm, has brought to the table something that the industry has really been asking for, is a simple solution where in one step you can cut and seal you know, filter media, things of that nature, different any non-woven type applications where you need to not only weld the perimeter, but you also want to cut the part out in one operation. But you know, really, there hasn't been an application where we haven't seen some benefit, and there's been some applications where, quite honestly, we couldn't do it without the servo welder. There's certain applications that have come across my desk, that came across my desk for years before we had one, that I would try every time it came across, and I'd fail brilliantly every time. And then once we got the servo welder and we're able to really stop the process, stop the motion, it changed everything. And these applications have proven to be quite easy, honestly, once you've got that capability.
Wow, that's awesome. So let's talk about pricing from if you get true 20 kilohertz applications, what would be a percentage difference in a price of a pneumatic versus an ultrasonic?
That's a good question. A little hard to answer. So from a a competitive point of view, when you're looking at, our competitors' highest end pneumatic systems to our servo system, we're generally a little bit less expensive than they are. Comparing to some of our lower capability pneumatic welders, you can be looking at another 10 or 15, 20%, depending on what the capabilities are that you're comparing to. I can provide you a very low end welder for a very inexpensive price that doesn't really give you much data back, doesn't really have much control, and if your parts really don't need it, and there's a tolerance for inconsistency, then we can provide you a welder that does that too. But if that's not the case, and you need consistency, and you need repeatability, and you need the increased strength, the servo welder pays for itself very quickly.
Yeah, I mean, with only less than a 15% difference, it's almost a no-brainer, especially because of the ease of reapplying it for other applications in your facility. So
definitely. And again, there is a solution to different applications that may be much less expensive, but again, when you look at the market, I think we're very competitively priced against our competitors' highest end pneumatic presses.
Sure, cool. So one of the things I always want to make sure that customers understand, if you have a weld application, what we prefer is an opportunity to weld those parts for you so that we clearly understand if we can solve the challenge that you have. And then obviously it helps us understand exactly what settings, what technology, what frequency we need to select and quote you for your application. So we really want to have those products so that we can either send them to St. Charles, which is our headquarters, or sometimes we send them up to Connecticut, where Mark is, to use his lab. But we have labs. We've got a lab just outside of Atlanta that focuses on our fabric applications, textile type of lab. So we've got any number of resources to help support customers. When you have an application, we want to weld it first so that we don't try to fit you into something that isn't going to be the right technology for your application.
Further to that point, Russ, I'd also like to say that if you've got an application that you're struggling with on a pneumatic welder, that you're having a lot of fallout, you're having a lot of inconsistencies, we have done this time and time again. Send me your parts, send me your tooling, even if it's our competitor's tooling. We will set it up on the servo welder. I will run a batch for you, and sometimes the proof is in the pudding. I can show you exactly what we can bring to the table by making the only change to your process being the welder itself.
Awesome. Yeah, for sure. Absolutely. We'll have all of our contact information for those that are watching this on YouTube or after the fact. That's where we get a lot of people tuning in to try to understand more about these technologies. So we have come up on our time. Is there anything else that you would like to add, Mark?
I think I covered it all, and I appreciate the opportunity to give this presentation, and look forward to doing another one at some point.
Yeah, man, you did a great job. So very technical, very detailed. So I think everyone definitely has a better understanding of ultrasonics in general, and then specifically how they can benefit from implementing a servo welder in their application. So as we always say at the end of these for our customers out there, we just can't thank you enough. We appreciate your business every single day. Our business does not exist without your business. So we are thankful and grateful for the opportunity to serve you every day. Visit us at capexsales.com. If you're watching this on YouTube, please like it, share it, get the word out about what we're doing here. Every Wednesday in IndustryCast, we are sharing either manufacturing new technologies, talking about technologies, or we are sharing some personal development for our engineers that we serve out there. We did 8 weeks of capital project management discussions. We did what we call a reset, where we work on setting goals each quarter. So we're going to do that on a quarterly basis to try to help you stay focused in advancing your career as an engineer. So that's our mission here. So We always want to be adding value. That's our tagline here at CapEx Sales. So if you currently don't receive our Wednesday reboot emails, please just go to our website, capexsales.com, and there you can sign up to receive our emails. As you can see, this email today was about our vision. The intent of that email is to offer some personal development, some things that we've learned, and we also obviously talk about technology and different things that are going on out there in industry and manufacturing. Have a wonderful day, and we'll see you next Wednesday at 11:30 Eastern time right here. To everyone out there that's paid attention, that's watched this, that's made it this point, we are grateful for you.